So, well, there goes my first joke. So, who am I? My name is Jeroen Domburg. Yeah, none of you is here for the first time, so you know who I am. So that would be my joke. What is this? This is a laser printer. No, it's actually a digital color LED printer. What? That's the name. I've also seen the name laser like, which is like, yeah, we really don't want to admit that it's not a laser printer because it would just confuse people. Brother decided let's just confuse the ever-loving crap out of people. I mean, these are color LEDs that have color LEDs? Is it like an RGB printer? Like you can get RGB RAM and RGB. Anyway.
So this is not new, right? Like Brunner has been doing this LED printers.
It's been around. It's been around. I'll get to that later as well. So how does a normal printer work? You've got your drum here, a very important bit. It's a drum coated with photosensitive material. You've got your laser here that goes over a rotating reflector that throws the beam out like this. Gets mirrored onto the drum. The idea is that the drum gets pre-charged with a 2 kilovolt corona wire that effectively drops an electrostatic charge on the drum. The laser, however, can sort of burn that away. Whenever the laser hits the drum, again, the drum is photosensitive, the charge will dissipate whenever the laser hits it. So by turning the laser off and on, you can selectively dissipate the charge or not. Toner here, static discharge does what static discharge does and will attract the toner. Toner will stick to it if there's still static charge. That goes through here. Paper enters here. Goes past the drum in a -2 kilovolt corona wire. The idea is that the wire will attract the toner from the drum onto the paper. It goes through a fuser that melts the toner into your paper, and you know you have your printout of your cat pictures.
What about the blade?
What about the blade?
Oh yeah, the blade is there to scrape off any toner that might remain, because otherwise you get like gray streaks on other things. This is what that looks like in a more realistic version. So laser, rotating mirror, optics, mirror, optics, and then the thing. So this thing is fairly big. That's the thing. And the thing with color laser printers is that they have red, green, and blue. No, sorry, different color space. Cyan, magenta, yellow, and black. Okay.
Yeah.
So the thing is, each of these things has a drum, and each of these things needs its own laser thing, and then you get like huge laser printers. And at some point, people want to have cute little laser printers that they can just put on their desk. So it's not good. So what do? We take the like the drum doesn't necessarily need to see a laser. It can have any light source. For instance, you can have a bunch of LEDs, and if you shine that on the drum, and you have the same effect, the charge will dissipate. So this is about 1 inch. This is 1, 2, 3, 4, 5, five dots per inch. So a printer needs a few more. So that needs to be about 1200. So I don't think I can get away with 5mm LEDs. Maybe 3? No. So the question is, how the hell did they do that? Did they use a hydraulic press? And, you know. So there's one way to find out. Well, there's multiple ways to find out, but there's one fun way to find out. And that's to buy one.
Oh, 15 years.
Oh, that's true. So yeah, it's like equivalent of 10 Singapore's dollary dues, whatever. It's a second hand from a Fujitsu, one of these things.
Sorry, just a question before, like a clarifying question. So, because of course you don't need 1200 LEDs in an inch. Can scan.
Yes.
So is this a stationary thing? Do you literally have a light bar?
This is a stationary thing. This is the size of 1 A4 paper.
Did you buy that pictorially or did you read words?
Google Translate has been my friend for over 10 years now. So. And also, by the way, taking these random numbers and chucking them into Google and seeing if there's actually a laser printer that comes out really helps.
But it really is a light bar.
Yeah.
It's just the power of LEDs. Oh, tightly packed LEDs. Are you gonna count each one?
So what you'll see that the black part here and the black part there is like the front, and there's like a lot of tiny lenses in there. It's not 1200 per inch. They have multiple LEDs per lens. But like lots of lenses. The lenses you can still see kind of sort of if you have good eyesight. The LEDs, the LEDs no way. So this actually sits very close to the drum. The LEDs shine on the lenses, and the lenses collimated to the drum effectively.
These
It's
are
a
don't look
photo,
at
so
them.
Yeah. So the
It's just
resolution is increased
have
by
one
having
line
some kind of
So
sorry, there's some kind of interference.
The
It's just an LED, a lens, and a drum, and the lens focuses it on the drum, so you get a nice sharp image rather than light going everywhere.
So this literally has 1200 LEDs.
Yes.
Okay.
Yeah, you can probably still see the
Is it really 200? I thought it would be more like 300, 400.
This one has 1200.
Seriously, yeah.
Yes. Okay. So 1200. Yeah. Like it's 1200, and if you do that times 4, then you could get a marketing material for 800. But like this is actually for a professional printer, so they don't pull that crap. Yeah, it's secondhand. I think it's kind of fallen off, but like when it came, it still had the remainders of toner. So from a working printer. Okay, continuing the story. Okay, so I immediately tore it apart without taking any pictures, which was kind of stupid on my part. But as you probably saw, lenses are on the front. On the back, there's a PCB. So I put those PCBs under my microscope and I scanned them in multiple iterations. And then I stitched them together. So these PCBs aren't really shaped like a banana. That's just stitched.
Artifacts. You fix it in post.
Yeah, technically. Okay, so what do you see? The back is here, the front is here. So as I said, I already did some dirty stuff to this thing before I scanned it. I should have been smart and done everything up front, but whatever. So this is where a 40-pin header used to be, which I actually in this case it went pretty well. You should have seen the other PCB because that only has half of its pads. There is this is a botch. This is a 3.3 volt LDO. There used to be a 3.3 volt switch mode power supply there, like a little buck converter, that seemingly has a maximum input voltage of 8 volts. Don't ask me how I know. There's some more electronics sprinkled on these are two dual MOSFETs, I think. Like there's only like Y1 or something on there, which is not precise enough for me to figure out what it is. But just from context, you can kind of sort of see that it's two MOSFETs in one package. These are all over the place, more or less. So there's 4 more here. There's a little resistor network here.
LED drivers?
So interestingly, like the only other big logic on here is this. And this is an I2C EEPROM. So it just has the serial number and maybe some calibration in there. And that's it. No LED drivers. So,
Maybe the logic is off point and the EEPROM is more to store data about the part itself.
Yeah, but like even how do you so this is like a total of, I don't know, 1200 times the size of an A4 paper. I only have a 40-pin connector. How?
Is it DRM or digital lockout?
I have no clue. I didn't even bother reading out the EEPROM, honestly. But this is like professional stuff. I imagine that is calibration values or something.
I mean, considering this is used in multiple different printers.
Also, it's a box standard I2C EEPROM. Like if it were DRM, it would be super simple to.
So is it Charlie plexed?
Even if you would Charlie plex it, we have 1200 times how many of them were there? I'm gonna say there's like 20, so that's like 24,000. Charlie plexing is like the square-ish of that, the square root-ish of that. Now,
How many places you can go?
sorry?
How many places you can go in the LED?
Actually not that many. Okay, let me continue before. So, this is the actual interesting bit. You might have overlooked it entirely, but this is the heart of the thing. You still don't see it? So, these are the things that are on the other side. Again, sorry for the bananaing, there's a big artifact here. These are little slices of silicon, they're chips. And these are chips that only have like 8 connections. There's 4 here and 4 here, so bond wires are here. I can tell you, if you accidentally snap it, you won't even feel it. So thin are those. And these are the LEDs. Yay, we found them. I have a microscope that can go up to this, but this is like the upper limit. So what do we see here? This is the thing cut in 2. So there's 4 pads here and 4 pads there. Zooming in, you can see a little bit more. These are the LEDs. We found them. They're tiny.
Quite tiny.
That's one LED for each bar over there.
This is more or less 1 LED per bar. So aside from that, we can also see the bond wires here, and we can see. Yeah, sorry, I have no clue. I can't read silicon that well, but you can actually see a few things. There's probably not that much logic there because these things are pretty big and there's not really space for it here. And you can see that there's a bunch of like bars running this way. And you can kind of see, if you look at this, that the LEDs are grouped in groups of 2, sort of, kinda-ish. But aside from that, who knows? So, we need to figure out what the hell this is in another way. So, yeah, I did figure out that it was actually LEDs, because while messing around with this and blowing up buck converters and stuff, I actually did accidentally manage to make 2 LEDs light up. These are 2 LEDs, actually.
Did they ever light up again?
Not until a lot later. So, how do you do that? Well, service manual is one thing. This is a professional thing, a great service manual. Maybe it has like schematics of the LED. But you know, it does actually have the LED thing here. Here is the LED print head. It is natural environment, just chilling out there. And you can actually see that this is a fairly compact thing. So yeah,
just one.
this is one of the 4. Yeah. So, and the service manual has a bit more. They're self-scanning light-emitting diodes, or SLEDs. Okay. Seemingly each strip has 506 points on them, so that's a fair bit. And it actually has a thyristor in there with one of the PN junctions work as an LED. So I've misnamed them. They're actually LETs, light emitting thyristors. Okay. So Google patents. Printer manufacturers love patents. So we now have a term, we dumped that in, and a long time, well, some looking up and filtering later, we get to this. This looks a lot like our laser printer. It has like little things that go to the drums, etc. This, well, you saw that looks like that. This is a picture. It's not entirely correct because we don't have this, but you know, it still looks like that. And it actually has a schematic of the internals. And here's a shift register. Like that's just diodes and thyristors.
Is the shift register made out of diodes?
Well, these are thyristors. That's actually the important bit. And it actually has some control signals. Only 4. I have 8 wires. So, you know, add a ground to it, add a power to it, and I'm still missing 2. So, so looking a little bit further, self-scanning light emitting device thyristor, like you just pick some terms from the patents and you dump that in Google. And the first thing you get is the patent, obviously. And the second bit is like a bunch of journals where they publish stuff. And of course, those journals are closed, so I went and actually bought the article. As we all do. And so you can see, like this is a more primitive version than the version that I have. This is let's say this is somewhere late 90s, so it hasn't been around forever, this technology, but it has been around for a fair few years. I need to actually look up the actual date. I wrote it down somewhere, but I forgot. So you can see the thyristors here. These are the light emitting thyristors. Thyristors have a PN-PN junction, so PN-PN. You can see that. And as a control thing, they just use a bunch of resistor networks and diodes, so not as complicated as the patent. So you can actually see that this was an earlier incarnation of the thing. So how does it work? First of all, who has no idea what a thyristor is? Okay, great. I'm going to explain it. Thyristor actually is a physical component as well. You can just go to whatever LCSC, DigiKey, or whatever, buy a thyristor if you want to. 3 pins. Kind of sort of works like a BJT, but a BJT, like a standard transistor, is like PNP or NPN. This is PNPN, so it has an extra layer in it. So how does it work? It has an anode, a cathode, like a diode has, and a gate, like a MOSFET has. So normally if you apply a voltage to it, it does absolutely nothing. It will refuse to conduct. It's only when you apply a voltage to the gate, then there's a little gate current, and there's like the thing starts to conduct. Now this is the same as a BJT, but unlike a BJT, if you remove the gate voltage, it still starts conducting.
A latch.
Oh,
And
exactly.
that's where the shift register part comes in.
There's some memory there. You can see that.
Is that what they use for those storage scope monitors? Those things that have persistent display.
Not that I know. The trick that they use there is that they usually, at least if you like the modern ones, just have RAM. The old school ones have actually a specific type of tube that applies a certain voltage to it using an electrode gun that scatters it around. And that means that any phosphor that is already touched will stay glowing. That's the way that works. Entirely different thing. Anyway, so if the thing conducts, you remove the gate voltage and it stays conducting. Great! Now how do you turn it off?
Yeah.
So the trick is you turn it off by turning it off. So if you remove the current, then it'll unlatch again. And if you then reapply a voltage, then you're back at step 1, and then it won't conduct. But in order to turn it off, you need to you need to turn off the current somewhere else. And then if you apply it again, it'll stay turned off. Okay. Great. Now we have this. There's a bunch of thyristors there. There's thyristors here. There's thyristors here, and like everywhere else as well. And there's a bunch of diodes and stuff. How the hell does this work? Well, the patents actually explained, but like patents are legalese, so I'm still not entirely sure if I understand it. So I'm gonna give my best, like what I understand from it. But there's a whole bunch of question marks here. Okay. First of all, these components in this schematic kind of look like normal components, but the fact of the matter is you don't need to go to DigiKey to buy off-the-shelf thyristors in order to put them in your chip. If you make a chip, you can make thyristors as simple and as complicated and as crazy as you want to. So for instance, these diodes don't have a forward voltage of 0.7 volt as you would expect. They have a forward voltage of 1.5 volts because, I don't know, they just made them that way. Same thing with the thyristors. These thyristors are not the same as those thyristors. There's a whole bunch of customization going on. Like if you were to build this schematic with off-the-shelf components, it wouldn't work. Secondly, the patents, etc., for some reason all work with negative voltages. Like these bits are grounded. Yeah, they're Christmas trees, they're upside down. And then everything else uses negative voltages. Yeah, so yeah, fuck that. These are all positive, 3.3. So for your to reduce confusion, I've inverted that. Okay, so say we start out with this. Don't ask me how we got to this situation. There's a start pulse going on somewhere. These are your clock inputs, more or less. This is your LED enable input. And for some reason, this thyristor is already conducting. It got turned out earlier. It got turned on earlier by something else. Now, we want to use this as a shift register. So we want to take this charge, this turned onness, and move it this way. So how do we do that? Well, one thing of note is that because this is a diode and it's conducting, so this is at 3.3 volt, this is at 3.3 volt, there's a PN junction here that is conducting, so this is also 3.3 volt because it's connected to the gate. That took me a while to get my head around, but like that's a thing. There's a diode here, and I told you before that these diodes has 1.5 volt-ish of forward voltage, which means that this one is at 1.8 volt and this one is at 0.3 volt. Now, these thyristors actually start conducting at like 1 volt-ish. The reason this thyristor is not conducting, even though its gate is at 1.8 volt, is that it's connected to something positive here. So this is positive, everything is positive. The thing is not doing anything because there's no current running. This thyristor again is connected to the one that is negative. So you would have a current running here, but this is only at 0.3 volt, so it still doesn't do anything. So this is static. If you leave this like this, it'll stay like this. So what if we change it? We ground this one. Well, what happens then is that this thyristor had a gate voltage that was high enough to conduct, so it will start conducting, and you now have two LEDs that are on. And what you do then is you disable this one. That means that your first LED is disabled, and now your conductiveness hopped like by one thyristor. And you can see if you do that over and over and over again, we'll just get the thing go through. So just to put the voltages in here again, this is at 0 volt, and the rest of the cascade has also moved. So this is 3.3, this is 1.8, this is 0.3 volt. Now, in this incarnation, they have put the LEDs like here. They're separate from the thing. They've drawn them as an LED and a thyristor. In reality, they're one and the same. You can now turn on the LEDs by grounding this input. If you ground this, then obviously this gate is at 3.3 volt and it'll light up. This LED will not light up because this thyristor is made slightly different, and 1.8 volt is not enough to make it light up. And the rest of the LEDs don't have a gate voltage, so only this LED lights up. So you can select which LED you want to light up by using these inputs, and then you can light it up by using that input. So, as I said, in reality, my thing doesn't have 6 connectors. It has connections. It has 8. So the way I made it work was by connecting it to an ESP32 and just generating random signals. Oh. Then it didn't work, and then I went to the datasheet and looked at the things. And then I sort of kind of tried to apply those waveforms to some pins and generated random signals in the other. At some point, I got something working. So this is what it looks like if you clock in like O1. So effectively, my idea was maybe I can make it work like a shift register. So it doesn't work like a shift register because all the LEDs share the same current. So the more LEDs you turn on, the lower the voltage you get. And at some point, you can just see that it doesn't turn on hard enough for the rest of the LEDs to turn on. So you know my idea of the most high resolution POV toy in the world, dead. But you know, I can still have fun with it. So, you know, if you have one LED that you can just send places, then you can now have the tiniest Larsen scanner in the world, to my knowledge. So the resistor is a quarter watt standard resistor, and it moves around that hard because I'm holding it in my finger, and at this resolution, everything moves. So yeah. If you want to see it, I've actually got the thing with me, and seemingly none of the wires broke. So, yeah, I can turn it on later.